Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment&Health. Eco-Environment&Health is a journal initiated by prestigious scientists with a strong editorial board, including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design, and broadcasting. The experts will accompany you like an harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Thank you very much, Wei, for the very kind introduction, and thanks, of course, also to EEH for the introduction to the seminar. Welcome, good morning or good evening, depending where you are. And in the upcoming 40 minutes, I'd like to guide you about a few ideas about nanotech in plant agriculture, and because it's also popping up pretty often about nanoplastics in plant agriculture. Let's get started maybe with one slide about our university. University of Vienna is pretty old. It's actually the oldest German-speaking university in Europe. It has 96,000 students, so quite big, and out of this, 6,400 scientists. We have 180 studies, 15 faculties, and 5 centers. And the center I founded together with colleagues is actually the youngest about environmental sciences and microbiology. Again, if you think about doing a sabbatical or postdoc or PhD in Vienna, Vienna is a very nice city. It has a lot of quality of living. It's pretty lot of old, nice buildings. That's our office for the ceremonies with beautiful Klimt buildings that are my daughters over here climbing, and here's Greg Lowry from Carnegie Mellon University. So you expect to hike a little bit if you're in Vienna. So it's beautiful, nice. It's a small country, only 8 million people. Yeah, 8 million, that's nothing. So Vienna has 2 million people. So it's a nice and small country, and research is pretty good. So if people are interested in coming to Vienna, just contact me. That's my group. A lot of people working over here. Group is international, and the group is only English speaking. We also only teach in English. So in the master level, there are no German courses anymore. And so it's everything taught in English, which makes it easier to hire internationally. Let's get started. So that's the outline of my talk. I would like to speak in the beginning about the challenge moving from 8 billion people as of last week. HWO said we have 8 billion people to 10 billion people by 2050. And then from there, move to nanotechnology in plant agriculture. And from there, talk a little bit about plastics in agriculture and some stories here, and then some take-home message. I start right into it because it might be late for you and you want to have your dinner, or you're just coming out of dinner, so I get started right away. Okay, so that's the projection of growth of population on our planet. So 2015, it was 7.5 billion. Now we are already at 8 billion, and prediction is roughly about 10 billion. The most recent scenario says that then it's declining again and population would go down. We will see 2050. This comes, of course, together with a significant increase in food production. So we need way more food by 2050. And estimates say that we need about 60% more food. And this is different for corn, maize, or beans. And so it's really a heavy burden. If you look to food production, which needs to increase, you can also see that this is the production of food at the moment. Yeah, that's what we need. And there is a gap. So we have a production gap, especially in countries with low income. And this is driven a lot also by the consumption of meat. I will talk about this later a little bit. So if you look to the numbers, 2005 to 2050, predicted increase in beef or mutton or pork, poultry, you see massive increase in meat consumption. As of today, about 820 million people have insufficient food, but on the same side, 1/3 of all food is wasted. 2 billion people are deficient in micronutrients, which is pretty important, and food production needs to increase by 60, but maybe of 100%. So food security and food safety is a major challenge of our planet. But food production is already the largest pressure, or think about climate. So 56% of the non-CO2 emissions are stemming from agriculture. So it's really huge production, methane basically. And then about CO2 greenhouse gas emissions, it's about 19 to 29%. So largest non-CO2 greenhouse gas emissions is from agriculture, roughly totaling about 30% of greenhouse gas emissions. And the impact of climate change on yield predictions are negative. So that's the yield, agricultural yield. That's a lot of different models run by Seeger. Most predictions show a negative trend. So with climate change, soils becoming more fertile, maybe in the north of Canada or Russia, does not outcompete extending of desert in other parts of the world. So the overall trends on the planet are negative if yield. So we have a problem here. Land use and biodiversity, you know, of course, that we are in times of biodiversity loss. That's really steep. That's also why we call it the Anthropocene. Biodiversity loss is highest ever seen. Yeah. 75% of deforestation is by agriculture, and agriculture already covers 1/3 of our planet. So it is big numbers, big fact. Water, food, energy nexus is central for development. If you look to the total picture of food production, about 30% of the total energy consumption, that's globally, it's 70% for the US, 70% of the global water use, it's 90% by 2050. And then 30 to 50% of the nitrogen fertilizers are used by plants, and the rest is lost to groundwater and air. So most of the fertilizers is lost. So we have some problems here too. And this basically is the overall picture from a paper myself and a lot of colleagues were publishing in Nature Food 2 years ago. We just made this picture. That's the burden we have already, yeah, on energy, land use, groundwater deforestation. But population is increasing and food production needs to increase. And food production basically hits all of the sustainable development goals. There's not a single sustainable development goal which is not basically affected by food production. I normally wouldn't read a text in a talk, but I like this comment from Tamara Lucas and Richard Horton on the EAT Lancet Commission report. And this is pretty heavy stuff. It's like civilization is in crisis. We can no longer feed our population a healthy diet while balancing planetary resources. For the first time in 200,000 years of human history, we are severely out of synchronization with the planet and nature. This crisis is accelerating, stretching Earth to its limits and threatening human and other species' sustained existence. So this report shows a grim outlook to the future, but also solutions. What do we need to do to increase food production? And the Eat Lancet report showed in a nutshell these topics here. First, raise productivity is the single most important step. So we need tech innovation. Link agriculture intensification with natural ecosystem protection. This means we need intensification, not expansion. That's a big topic here in Europe, where we also think about organic growing and less intensification. This will not work globally. So we need intensification, less emissions from fertilizers and plant protection products. Reduce greenhouse gas emissions, spur technology innovation, very important. Manage demand, of course, which means reduce food loss and waste, and shift to healthier diets. So unfortunately, the message is clear: low to moderate meat consumption. We eat too much meat. Yeah, the planet cannot afford the amount of meat we are eating. Nano-enabled plant agriculture I'm talking about is, of course, not the one single solution. That's clear by the problems, but it has great potential and might add to other technologies. So it's an add-on. It might be important. So we are already here in the talk, nanotechnology in plant agriculture, and I would like to show you what's in the market and what will come. So nanotech, most of you, I think, will know it's the new wonder material for about 30 years, many applications, your computer, your mobile phone, electronic devices, solar cells. So nanotech has a lot of applications. So from health to consumer products, daily life, all over is nanotech, food packaging, but also it's coming more in plant agriculture. And this, of course, makes a big difference because it's massive scale. This is a topic which has been debated like 15 to 20 years ago, much in gray literature. So if you look here, there's a lot of report, a lot of gray literature, and it is claimed that it has the potential to revolutionize agriculture. But we have not seen it so far. So what's the problem? So we have a controversial discussion on risks linked to nanoculture, and I would like to dig a little bit deeper today in nanotech in agriculture. What is the principle? The principle often is that you have a selective nanocarrier, and this nanocarrier delivers a cargo at demand. The at demand is very important. So that's your carrier here. Yeah, it's like your rocket. Might be silica, might be carbon nanotube, might be gold, a quantum dot, a magnetic nanoparticle. And then you charge it with a cargo like a pesticide or a fertilizer or DNA, a protein or an activator. And then you, for example, have a release of fertilizer on demand. Yeah, the idea is it doesn't go to the groundwater, or you deliver micronutrients. Or it delivers target-specific a pesticide, or, for example, DNA to a chloroplast. Or you can do in vivo labeling and imaging. And for example, that's an example from the Strano lab at MIT, where you see that chitosan coated single-walled carbon nanotubes deliver the cargo, the RNA, inside the chloroplast. So the technique works. It's interesting. So you get it on the cell, it passes the lipid membrane, it enters the chloroplast, and finally it is delivered inside the chloroplast itself. So it really works nicely and has a lot of potential. What do you see on the market? Also is nano plant protection products. So for example, Asteroid FC from Wivecop or DuPont Coeseed or other products. So some products are on the market, but don't get offended, but they're not so smart at the moment. So this release, when you need it, the targeted release, we are not there. We would need to have the release exactly at the time point where needed, where a sensor detects the pest. So there's a lot of research to do, but there are also interesting applications. Fertilizers and nutrients, I tell you first why this is so important. You, of course, know that 50% of all nitrogen is lost. You might also know that over 90% of the phosphorus, which is mined globally, is going to agriculture. So both nitrogen and phosphorus, they are planetary boundaries, yeah? And this is by agriculture. If you look to Earth history, if you look to anoxia in oceans, this was always linked to high phosphorus inputs. So most of the phosphorus and nitrogen is going to the ocean. So of course, if you could change this, if you could make the use of nitrogen more efficient, yeah, more than 50% is lost to the atmosphere with laughing gas or to the groundwater as nitrate. If you can make this more efficient, this would help a lot. But also micronutrients. Micronutrients are of major importance, and I talk about this a little bit later. Nanosensors and chips, that's cool in a way, yeah. So not much risk here. So for example, plant status, or enzymes, soil growth conditions, pathogens, contaminants, identification. So what you have an analyte, let's say drought or a contaminant or the plant status. You have a bioreceptor, an enzyme, an antibody. You have your nanoparticle. Yeah? Then you have the transducer, electrochemical or optical or mass, and then you have a signal. So for example, this is here from Michigan, from 2 examples from the Day Lab as MSU here. Or biosensor lab, also MSU, for example, where you can detect with a magnetic iron nanoparticle E. coli. Yeah? And the idea would be that then in spinach, you can find E. coli. This is heavily important, I think. It's 120 billion per year in the US health costs for this illnesses. Or you can detect listeria basically with a magnetic antibody, which is here at the nanoparticle, and then you have lateral flow analysis and can detect listeria. So a lot of applications or plant diseases. So nanosensors and chips, I talk later where we see the perspective for this. So we wrote a perspective paper, yeah, and if you don't have access to Nature Food, I share the tiny URL over here. You just need to remember this last numbers here, or write me an email and I can send you the document. And so we published a paper about technology readiness and overcoming barriers to sustainably implement nanotech-enabled plant agriculture. So this is an expert judgment. So you can criticize this. We just did our judgment, what we think. What do we have here on the y-axis? On the y-axis, we have the technology performance level. We said that here there's no or moderate improvement. Here we have significant improvement, and that's a game changer. So that's the technology performance level. And this level here, the x-axis, is the tech readiness level. So we said, okay, proof of concept, lab testing, field trials, validation. So let's look at points where, and we might be wrong, it's just an expert guess of all these people here involved. Yeah, we just said that soil conditioning, we have trials, but what we see is not so promising. On contrast, if you look to nano-carrier-bound gene editing, this is probably a game changer and heavily investigated. Also because regulation is very different. If you look to the US and to my understanding also in China, because this is not changing the DNA to the next generation, this would not be considered GMO food in the US and in China. In Europe, it still would be considered GMO food. So this is a big difference, but you can really introduce new treats in a plant, which might be very important. More advanced is nanocarrier-bound RNA interference. Since Corona, everybody knows what RNA is. So RNA interference is a very important plant protection mechanism. And this is going ahead. So this is getting very interesting. And I would also say nanocarrier-bound micronutrients might be important. If you ask me 2 years later, I would maybe scale this down a little bit and would scale up the micronutrients. So the research of the last 2 years on micronutrients show that they really have a good and big potential to increase yield or defeat pests. And then nanoactives and nanopesticides, they are on the market and they might change things really. The overall opportunities for nanotech and plant agriculture, plant protection. So what you need for plant protection, this is the pesticides, actives, and growth enhancer, you need smart delivery, smart release. Yeah, slow is not enough. This has been debated over a long time. So it's not essentially enough to just say my pesticide is released slower. Yeah, this is done by PE coatings or something. You need a higher efficacy. You need to reduce the loss. Yeah, you really have to turn this knob to make it 20% more efficient, and then it's worth. Nanofertilizer is getting interesting. Yeah, it's changing here. Deliver where, when, and what is needed. Reduce loss. Yeah, much work has been done on micronutrients in the last 2 years to suppress diseases or increase stress tolerance, stimulate photosynthesis. There are very good papers, many options: nano copper oxides, copper phosphorus, copper sulfides, molybdenum, and zinc and cerium, or biopolymers for nutrient delivery. So I would say this work here has even increased in the last 2 years. Sorry. Sensors, yeah, smart. I think probably best at high value crops. Yeah, there's less concern because you don't eat them later. So sensors could be very interesting. And genetic engineering, of course, has the highest potential, but highest concern, and regulations differ. So nanocarrier facilitated delivery of genome editing, for example, when you have transient and controlled Cas9 expression without incorporation of foreign DNA. And that's the point. You don't have the incorporation of the foreign DNA. And for regulation, this means that this might not be GMO food. Or you have topical application of nanostabilized double-stranded RNA to induce RNA interference as plant protection mechanism. So that's also a thing which is heavily investigated recently. How to overcome barriers. We also discussed how we can move forward. Details are here in the paper. Precision spraying makes sense. Yeah. Aerosol mediated applications, leaf dipping, this is done. Targeted delivery, smart material selection. Don't start with something which is toxic from the beginning. Controlled exposure. You need sentiment science, and of course, you need a lot of involvement and discussion with consumers. I come back to this in a summary, because there's, of course, also the risk of nanotech in agriculture. And the risk using nanotech in agriculture, it's large scale. Yeah, you talk about 1/3 of planet Earth, and this needs to be evaluated very critical. So the perspective of the consumer and differing regional and global perspectives needs to be taken into account. What I like to say is that what works, for example, in Europe or China does not necessarily need to work in the US or South America. So you need the discussion with the consumers and with the producers. And of course, there are a lot of questions on risks, on exposition and hazard. My recommendation would be start here on the hazard side, that the hazard is low of the materials you use. So this would be the most important thing. And then questions like what is impact on nutrient quality, transgenerational study, trophic transfer studies, chronic low dose exposure data, or effects on the rhizosphere and biota. So that's quite important. Jason White is doing a lot of work over here from Connecticut Agricultural Research Station. On the other side, my group, we worked for 15 years in risk assessment of engineered nanoparticles. So there are, I would say, 20 years of environmental risk assessment for engineered nanoparticles. Yeah. And we gathered a lot of knowledge. There are 10,000 plus publications on risk assessment for nano. So we do not need to start from the beginning. Yeah. Much will be transferable to nano-enabled agriculture. There are a lot of monitoring. This is from Klaus Svensson here from the UK, a project we have been involved in, where you combine basically the emissions from productions, from shipping in the consumer, and then how does this move in the air, in soil and water, and what is the risk in which pictures. And you can do the same principle for nano ag. So there is a lot of research there. You don't need to start from the beginning. There are thousands, 10,000s of publications. I summarize the lessons learned from 20 years risk assessment of nanotechnology in consumer products. And there's a developing consensus that ENP may pose a low environmental risk. So high risk are not expected, but because, no scientist without but because of uncertainty and lack of data in many areas, definite conclusions cannot be drawn. Well, ask a scientist about definite conclusions, you never get this because they are not there. Question is, can this be transformed to nano-enabled agriculture? I would say in most cases, yes. There are questions on the right data for a holistic One Health approach, chronic low-dose exposure, trophic transfer, transgenerational studies, containment of exposure. I mean, in vitro exposure and tox testing might help a lot, but this has to be done. And then translation of incomplete understood science into regulation and policy is challenging. We know this with the corona crisis now for 3 years. Scientists never completely understand things. This is impossible, yeah. But then getting this into regulation, you see how difficult this was and is with corona. It's heavy, so there's a lot of political work needed. And integration of technology innovation and risk assessment is needed to ensure that the benefits of the technology are gained with the minimization of possible effects. I mean, that's clear. So I would say innovation and precaution are equally important, absolutely. My personal message would be also only go nano if nano is needed. If you don't need nano, yeah, it is expensive. You need a lot of energy, yeah. You have to do the risk assessment. So ask yourself in the beginning, is nano needed? So ask the question, is my effect nano-specific? So only go nano if it is needed. It doesn't make sense just to go nano because it's a beautiful word, it sounds better. Just do it when the nano effect is there and is the driver. In case of agriculture, covering 1/3 of Earth's terrestrial surface, you need to do it right. So you need to be careful with this. From here, I would like to go to the last part of the talk. We have roughly about 10 minutes and this will work out. So it's not directly connected, but it's indirectly connected. And I will show this in a minute because questions are the same in agriculture. I will specifically talk about contaminant transport with plastics. So you have seen this slide before, yeah? Agriculture in the Anthropocene. And now I just added myself and plastics. Raise productivity is the single most important step. I just read this sentence 20 minutes ago. And of course, plastics play an important role because productivity, if you think of greenhouses, if you think of mulching films, extending the growth season, yeah, mulching films, plastics are used heavily in Europe, in China, in the US, all over. And then the second sentence I was reading, link agricultural intensification with natural ecosystem protection, yada, 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 less emissions. Well, plastics help a lot with intensification. And they help, of course, lower the emissions because you need less fertilizers, less plant protection products, you need less water, you have less greenhouse gas emissions. Spur technology innovation, I will tell you later, this is heavily needed for plastics, and then manage demand, reduce food loss. Yeah, food loss, packaging and plastic is important. So my message is that plastics play an important present and also future role in plant agriculture. You probably know the UNEA 5.2 treaty, which means that in the next 2 years, we want to find solutions globally on plastic. So this is heavy negotiations and heavy pressures going on. And there is, of course, a lot of discussion if plastics should be out of agriculture. My personal viewpoint is this will not be the case. We need it for irrigation, we need it for climate change, for extending the growth season, but a lot is going wrong with plastics in agriculture right now. Where's plastics used? So just have a look here. So for example, you have polymer-coated fertilizer with PE or LDPE or cellulose. Yeah, cellulose might not so be problematic, but if you have PE, polyethylene is not degraded, end of story. Yeah, you cannot degrade PE. This is not happening. So these PE coatings will stay in soil. You have fertilizer sacks or bulk containers, seedling plug trays, nursery checks, and then here in red, mulching films. Mulching films dominate the plastic market. You have LDPE, but you also have polyvinyl chloride, yeah, which always contains phthalates. So, and they can normally not be recovered, and they can never be recycled at the moment. And so often this is tilled into the soil and changes the soil physical properties. But once again, we have the same problem like in the beginning of the talk. We need to increase food production. So you cannot easily say, okay, just get rid of the plastics. We have 20% less food production. At the same moment, we need to increase food production. So we really have a wicked problem over here. Textile, greenhouses, shade and protective nets, irrigation strips, of course, irrigation pipes, support tiles, maybe not so much, some sacks, storage crates, but also like pesticide containers. To give you some numbers, intentional inputs, it's about 12.5 million tons per year. And this is heavily increasing. That's data from last year FAO report. 50% of the market, 40 to 50% are films. Yeah, that's for most countries. Soil is the dominant receptor. And crops, it's not fishery and forestry, it's crops, it's the largest user. And lifetime for some users is very short. If you think about mulch films, yeah, the overall lifetime is everything less than a year. In addition, you have unintentional inputs with biosolids, tire wear, for example. I talk about this at the end of the talk, wind and recycled wastewater. So here we go. I will address today only are micro and nanoplastics a vector for contaminant transport. I do so because this is very often debated, and I give you the answer right away, no. But as a scientist, I say but. So what is the story? The story is that, for example, you have a wastewater treatment plant here. Yeah. Also, you have, of course, tire wear coming from the road runoff. Yeah. And then you have the biosolids with tire wear particles. And then the tire wear particles here with your biosolids might go to the field. Or you have mulching films, they degrade, and then there are plastics, or you have your agrochemicals, the agrochemicals might adsorb to the plastics, and then these contaminants here might travel with the plastics down to the groundwater. And that's something which you read very often in papers, for example, that you say, okay, plastics, especially nanoplastics, might, due to the large surface area, enhance contaminant transport in soil. And we published this paper in Nature Earth Communication, Nature Communication, Earth and Environment, I think beginning this year. And you have two processes which you can separate. The first process is your system is in equilibrium, which means your contaminant, which is linked to the plastic here, desorbs. The smaller the particle, the faster. And then finally, it is desorbed and adsorbed to the soil. Or you have a fast transport, decoupled. And then the contaminant is here inside, but the transport is so fast that it still stays on your plastic. Case number A, if you reach equilibrium, your contaminant is lost, it's going to soil. So finally, the plastics will not play a role. Case number B here, your microplastic will add to the contaminant transport. This picture here is a little bit busy, and because it's late, I don't run you over it completely. Let's just focus on these two here. Just focus on this here. So the one thing is go to dinner, it doesn't matter. And the one thing here, it is relevant. So that's the first situation. You have your contaminant loading on your nanoparticle. Yeah, that's the contaminant on your nanoparticle. And then just while travel time, it desorbs out of your plastic. And because simply you have so much more soil and so much more water than plastic, the equilibrium partitioning will go on the side of the soil. So finally, the plastics will not transport any more contaminants. Yeah. Or the other situations, this is a pretty fast transport. Yeah, soil could happen. And then the contaminant sticks to the plastic, and then it will transport your contaminant. It will not go to the soil. And of course, from 101 civil engineering, you know that this is nothing else than the Darmköhler number. So the co-transport depends on the particle size, distribution coefficient, residence time. So it is the transport versus the desorption timescale. So you can just calculate what is faster. Is desorption faster? Then it's equilibrium. Or is transport faster? Then it's decoupled. And that's the Darmköhler number. And you can say Darmköhler numbers smaller one, then it is relevant. It's decoupled, or Darmköhler number larger than 100. It's not relevant. And we published a paper for engineered nanoparticles. I think this was 7-8 years ago. Nice cited. And I felt we have to do this again for plastics. We did, of course, completely different calculations. That's the summary. I run you over this slide because it's not easy to read. So what we did is we checked, this is your plastic particle here. Okay, that's the plastic particle. And then we checked do you have intra-particle diffusion? Is your contaminant diffusing out here? And is this the rate limiting step? Yeah, just say you have a PEH or a PCB or a pesticide inside your plastic and it wants to diffuse out. This could be the rate limiting step. And then this is the equation for diffusion. So you need the apparent diffusion coefficient, you need the radius, you need the tortuosity, and you need the radius goes, of course, into the equation r squared. Yeah. Or that's the other possibility, is it aqueous boundary layer diffusion? Every particle has an aqueous boundary layer around it. So the rate limiting step for the kinetics could also be the aqueous boundary layer diffusion over here. So then it would be this equation here. Don't get tricked that this only depends on the radius, because in this parameter here, for the thickness, the radius is in again. So again, also this depends on r squared. Take home message to make it very simple. We calculated intraparticle diffusion for particles 1 micrometer and for particles 100 micrometer. And you see that for all combinations we had of polyethylene, polystyrene, PVC, PDMS, or tire materials, and all contaminants we found in the literature, yeah, we found that simply forget it. You never reach decoupled conditions. You're always at equilibrium, which means you can go to dinner, it's not relevant. If the rate limiting step would be aqueous boundary layer diffusion, then for a few sets of contaminants, like here PCBs, but that's not the most typical thing on agricultural soils, you see, yes, PCBs matter. Okay, here for polyethylene, we have the most data for polyethylene until 1 micrometer. But if you go to smaller particles like nanoplastics, again, forget it. They will not play a role. So the story is very short. Nanoplastics don't play a role for contaminant transport and soil. It's just like, it's not possible. The but. So the but is what might happen, and it's just the few last slide, what might happen if there's no co-transport? It means that your contaminant leaches out to the soil. They leach, very simple. And that's the experiments we were just doing recently, and I just checked half an hour ago if the paper is accepted. We submitted the paper to ES&T. Reviews came back. Reviews are very positive. We answered all the questions, resubmitted it a week ago. So honestly, I'm expecting every day to get the paper through. So because we could answer all questions from the reviewers. So paper will come out this week, hopefully, and I can send you the link if you like to. So what we did, we used tire wear additives because tire wear is massively brought with biosolids or wind to agricultural fields. And we looked to tire wear additives. If the tire wear additives are taken up to the leaf, to the edible part of the leaf, yeah, and this has been lettuce. So that's the experiment. We look to these tire additives. If you're working with plastics and tire additives, you know that they're of much concern. Diphenylguanidine, bitranthocin, HMMM, 6-PPD, and especially the 6-PPD quinone, which is known to be toxic. And there was the science paper last year about Soho salmon in the US, about an Arctic, about 6-PPD quinone, pretty toxic. So we analyzed these additives here from tire wear and looked what happened. So what do you see over here? Left side. Left side is the translocation factor. It means what ends up in the leaves and what is in the roots. And what you see is that HMMM, this compound, I go back one slide, this compound here, which looks very strange, it has a sweet spot in the partitioning coefficient to pass the root epithelium, and it ends up in the leaf. So the translocation factor of 10 means that you have 10 times more in the leaf than in the root. Opposite, the 6-PPD quinone, yeah, it's very hydrophilic. It doesn't pass the membrane, so it stays basically in the root. And then here on the right side, you have it exactly the other way around. That's the root concentration factor. I'm sorry that the colors have been changed. The colors, a PhD student arranged it always like that, the lightest colors on the top. Here you see that in the root, 6-PPD quinone this has the highest concentration in the root. So it stays in the root, but it also goes up to the leaf a little bit. Yeah. For DPG, I can show you a typical picture. I could show it for all, but then the talk is too long. So you see a concentration in the leaf going up. That's leaf concentration. And then it's going down, which is metabolism in the plant. So it's metabolized because the plant wants to get rid of it. So this is for the spike dosing. So if you have a spike dosing here, it goes up, but then it goes down again. So we did a second experiment, different uptake pattern spike versus the constant dosing. So what we did here is we now put the tire wear particle into the hydroponic experiment. So it constantly leached out. So it was not a spike dosing, it constantly leached out of the tire wear. And what you can see then is in the leaf that DPG goes up, but also the quinone, the 6-PPD quinone and the 6-PPD, they end up in the leaf at a lower concentration, but they end up, same for the HMMM. So all substances basically end up in the edible part of the plant. And that's, of course, concerning. So take-home message, I'm pretty good in time. So take-home messages from my talk today is agriculture will need to intensify it. Nanotechnology and plastic both will play an important role in the future and help to reduce food waste, energy, water, fertilizer, and pesticide use. The number of papers on nanoparticles in plant agriculture is growing, but we haven't seen the breakthrough so far. Still, I see huge potential. I think in a few years we are there, especially micronutrients. I think it's hot. Risk needs to be evaluated very carefully. First, large-scale intentional use of nanoparticles. Yeah, it's 1/3 of planet Earth, but there's much transferable knowledge from over 20 years of nano environmental risk assessment. Nanoplastics, I want to make this statement here, are not an important vector for co-transport of chemicals. Forget about this, to deeper soil layers and groundwater. But the but is additives are of concern. They will increase the total flux of xenobiotics to environmental systems and might meet you later at the dinner plate. Yeah, innovation needed. Innovation is we need better additives. Less toxic additives, non-toxic additives, and biodegradable additives. And then also innovation is needed for non-retrievable plastics. They are of concern, mulching films. It is simply too much, 6 million tons, to just till them into the soil. Yeah, this doesn't work. So the solution here is recycling, yeah, retrieve it from the field, or recycling, or biodegradable. So much research is needed on biodegradable plastics. With this, I would like to thank you very much for listening, and I'm very happy to take questions.